morning. Today we're going to start our discussion on Chapter 16. In this chapter, we're going to be looking at an area of chemistry known as electrochemistry. So this is the area of chemistry where we deal with chemical reactions that have the ability to produce electricity. Now, what that really means is that they involve electron transfer. They involve movement of electrons. And this movement of electrons can be harnessed to create electricity. Now, we use electrochemistry in a lot of applications. Probably the most well-known are things like batteries, which may be contained in things like electric cars, or your classic C, D, AA, AAA batteries, or newer lithium-ion batteries that you may have in your computer or your cell phone, along with things like fuel cells. Right? Fuel cells are used in various applications. The picture here, right, is a very old fuel cell, one of the original applications, which are in spaceships, space travel. So going back to the early days of space travel, right, they used fuel cells to power certain systems within those spacecraft. Now, these are just some of the applications. We see a redox, or what we call electrochemical reactions, in lots of sort of everyday processes, like rusting of iron or burning, right? So you might recall that we talked about combustion reactions in an earlier chapter, and combustion reactions are a type of electrochemical reaction. Now, another term for electrochemical reaction is a redox reaction. And that term redox comes from the two processes that are involved in an electrochemical reaction. And that is reduction, which is the gaining of electrons, and oxidation, which is the loss of electrons. So within these electrochemical reactions, or redox reactions, one element is losing electrons, another element is gaining electrons, and this is where we get that transfer of electrons. These two processes have to occur simultaneously, right? They have to occur in conjunction with each other. Because if a substance loses electrons, they must go someplace. Some other substance must gain those electrons. Now, two other vocabulary words. So two other key vocabulary words that we need to understand are what are called the oxidizing agent and the reducing agent. So one key thing to understand right at the beginning is that these agents are both going to be reactants, right? They will always be reactants and never be products. And these come from the language of, one of the reactants causes this to happen and one of the reactants causes this to happen. So the oxidizing agent, right, and the agent there is the reactant that causes oxidation. Now, another way to think about that is that it contains the element that is reduced. So some things to keep in mind is that individual elements are oxidized and reduced, right? They undergo the processes. The material that contain those elements are the agents. So we'll get into that when we do some examples. So the oxidizing agent is the reactant that causes oxidation, and therefore it contains the element that is reduced. The reducing agent is the reactant that causes reduction. Therefore it contains the atom that is oxidized, right? So by being oxidized, it causes something else to be reduced. So we have oxidation and reduction, which are the processes occurring, and then we have the oxidizing and the reducing agents, which are the reactants that are involved in the reaction. So let's kind of summarize these terms again. So first, I want to point out a couple of mnemonic devices that may or may not be helpful. If they are, use them. If not, don't. But the one in the book is this: oxidation is loss, reduction is gain, oil rig. An older one is Leo the Lion says Gur, where Leo, lose electron oxidation, Gur, gain electron reduction. So again, oxidation is loss of electrons, reduction is gain. Oxidizing agent, substance that is reduced. The reducing agent is the substance that is oxidized. Now, in many redox examples, it is a metal that undergoes oxidation. So if we think about some trends, metals like to be oxidized. Whereas metal ions like to be reduced. Non-metals typically like to be reduced. Like, this would be things like O2, these kind of things. So if we look at some examples here, we can see that within the reaction of lithium plus O2 goes to lithium oxide, we have lithium that's undergoing loss of electrons or oxidation, right, as it's forming the lithium plus ions that are in lithium oxide, and the oxygen is gaining electrons, undergoing reduction to form the oxygen 2 minus ions that are present in the lithium oxide. So some other examples might be iron here undergoing oxidation, where iron is going to iron. So this is going to be iron plus 3 and O2 minus, right, in our ionic compound. So iron is being oxidized. Oxygen is being reduced, right, from 0 to 2 minus. So in a lot of these compounds, it's pretty easy to see what's going on if we have a metal and a non-metal involved, right? And this is one of the classic types of redox chemistry, where we have some metal plus oxygen going to a metal oxide, an ionic compound. Now, other reactions like this, right? This is a redox reaction, right? This is a combustion reaction like we saw in the previous picture. This is an example of a redox, but no ionic compounds are formed. So it's fairly difficult here to figure out what's gaining and losing electrons without some sort of system in place. And so that's what we're going to talk about next, is how we could possibly keep track of reactions like this. So the way we keep track of these reactions, or keep track of the electrons more properly, is using something called oxidation states. Now, we assign oxidation states to all the elements in a reaction so that we can figure out what's undergoing oxidation and reduction. So we can keep track of them. This is a bookkeeping, right? We can track where the electrons are and where they end up. So the oxidation state, or sometimes called the oxidation number, is computed for each element based on its ability to attract electrons. Now, we have a set of rules that can help us to do this, right? A couple things to remember though, they are not real charges like we see in ions, like in an ionic compound, right? So the elements within these non-ionic compounds are not charged. We're just looking at, do they have more or less electrons than what the ideal situation might be? So at this point, we're going to look at the rules that we use to assign oxidation states. So there are 5 rules, and they are what we call hierarchical, meaning 1 outweighs 2, 3, or 4. So the first 4 are pretty straightforward. If we have anything in its elemental form in the reaction, for example, like O2, or a metal like iron, these are in their elemental form, they're going to be assigned an oxidation state of 0. If we have a monatomic ion shown in a reaction, so let's say we show, say, nickel 2+, or we show Cl-, right, as part of the reaction, then those actual ions will get their charge as their oxidation state. Now, 3 is probably one of the most important rules, in that for a neutral molecule, the sum of all the oxidation states of its atoms must add up to 0. For a polyatomic ion, the sum of all the oxidation states for all the atoms in that ion must add up to the charge. So for example, if I have nitrate ion, then the oxidation states on the 3 oxygens and the nitrogen added all together must add up to 0 or to -1. If I have something like water, the oxidation states on the 3 atoms must add up to 0. So that's what we mean by that. If we have an ionic compound and it happens to contain a group 1 metal or a group 2 metal, then group 1 metals are given an oxidation state of +1. Group 2 metals are given an oxidation state of +2. Okay. So pretty straightforward so far. Now, the last rule deals with how do we deal with non-metal atoms within a compound. So there's a set of non-metal groups that we assign priority to. So these are in priority order, and this really is going to help us determine which non-metal is going to get the negative oxidation state if we have more than one non-metal in a compound, like we will in a molecular compound. So you can see that fluorine has the highest priority, and it would be assigned a -1 oxidation state. Now hydrogen is in here, but it doesn't really have to compete with anything, and it's always given a +1 oxidation state in a compound. Oxygen is special, has a high priority, it's given a -2. Now, the next one is other halogens. Other group 7s besides fluorine would be given a -1, right? Other group 6 elements besides oxygen, so sulfur, etc., would be given a -2, and group, this should say group 5 atoms. There's a typo in the table. So these would be things like nitrogen, phosphorus, etc. They would be given a -3. But what we see here is, let's say we have nitrogen and oxygen in a compound. Oxygen is going to get the negative charge because it has higher priority over nitrogen. So that's how we're going to use these rules. So the last thing that I want to do before we leave this section is to do a few example problems. Okay, so now let's look at a few examples. So our first example here is going to be the reaction of calcium plus water goes to calcium hydroxide and hydrogen gas. So if we were to go through with our rules, and so this one I can kind of diagram out, we look at calcium here. It's an element, right? So it's given an oxidation state of 0 here. Water, so it's a compound. And so within that compound, we use our non-metal rules. So hydrogen is going to be given a positive 1. Oxygen is going to be given a -2. Now, one nice way to keep track of these things, right, is we have a compound, is if I list all of the elements within that compound, and I assign their oxidation states, -2, -2. If I add all that up, of course, it has to, whoops, oopsie, miswrote that, sorry. We're going to have another H and another O, +1, -2. All of these add up to 0, just as like the charge on the compound. If we go over to our product side, we have calcium, which is a group 2 metal within a compound. It has a +2 charge, following our rule. Oxygen has a -2 charge within the compound. Hydrogen has a +1 charge. And so just to make sure that everything works out, right, if we write all this out, we have calcium, we have 2 oxygens, 2 hydrogens. The calcium is a +2, each oxygen is a -2. We have a +1 for the 2 hydrogens, and all of that, we have a +4, -4. Everything adds up to 0, as it should. And we have hydrogen H2 gas in its elemental form, right? That's a 0 oxidation state. So now we look for changes, right? We look for changes between an element on the reactant side and that same element on the product side. Now, only 2 elements are going to change, so there's going to be elements that don't change. So if we look at calcium, it starts out at 0 and it goes to +2. Well, the charge getting more positive, right, is a sign of oxidation, right? Because as you lose negative charge, right, you're going to get a more positive oxidation state. So that's another way to look at it. If we look at the hydrogen, goes at +1 and goes to 0, right? It's getting more negative, right? It's going down, right? It's going from +1 to 0 when it's gaining that negative charge. So it gets a more negative oxidation state. And so we can find the oxidation and the reduction. And if you notice, oxygen doesn't change, right? It's -2 on both sides. So we can say that the calcium is oxidized and the hydrogen is reduced. Now what about your agents? So remember, the oxidizing agent contains the element being reduced. So if we said that hydrogen is reduced, then the reactant that contains the hydrogen is the water. So water is the oxidizing agent. And the reducing agent then contains the element being oxidized, and that would be the calcium in the form of calcium metal. The calcium metal is our reducing agent. So that's how we can do that. Now, the last example I want to do here is a little bit more complex reaction that I have listed here. So I'm going to go to the next page where I have this written out. And we're going to go through this process. So, tin being an element, pretty straightforward, right? It's going to have an oxidation state of 0. Now, within this compound, we have HNO3. So if I write out my H, my N, my O, my O, my O, I know by rule that hydrogen has to be +1. Now, both nitrogen and oxygen would like to be negative, right? -3 and -2 here. But of course, they all can't. And we should remember that oxygen has the priority, so it's going to get its -2 charge. So what comes of nitrogen? Well, nitrogen will take on whatever oxidation state is required for this to all add up to 0. And so, At this point, we have -6 and +1. So in order for this to work, the nitrogen has to be +5 for everything to add up to 0. So we have +1, +5, -2 for our 3 elements. Now we go to tin oxide. We have tin, oxygen, oxygen. So the oxygen by rule is going to be -2. Now we don't have a rule for tin, but again, we know it has to add up to 0. So the tin has to be +4. We have NO2. So similar to what we saw before, the oxygen is going to take priority. And so the nitrogen has to be +4 to make it all work. So we have water. All right, water is nice, it's always the same. +1, +1, -2. So we've assigned everything. So now we have to look at what changes. What undergoes oxidation, what undergoes reduction. So if we look for things that change, tin. Well, tin clearly changes. So tin goes from 0 to +4. Well, that's getting more positive, sign of a loss of electrons, or oxidation. And remember, metals are likely to become oxidized, right? That's what they like to do, to go from their metal form to their ion form. And we look at what else changes. Well, hydrogen, it's +1 on both sides, right? Oxygen, always -2 on both sides in this case. So that leaves us with nitrogen. And so nitrogen goes from +5 on this side to +4 on this side. So we're getting more negative, right? We're gaining negative charge, right? So it's going from +5 to +4. So that's going to be a gain of electrons, a reduction. So we have tin being oxidized, and we have nitrogen being reduced. So the oxidizing agent, right, contains the material being reduced. So it causes oxidation, contains material reduced. So nitrogen is what's reduced. So HNO3 is where the nitrogen's at. That's going to be my oxidizing agent. My reducing agent contains the element being oxidized, or the tin, so it's just tin metal. Okay, so that's where we're at this point. We want to know how to assign these oxidation states, figure out in a reaction what's oxidized, what's reduced, and what our oxidizing and reducing agents are. So that's going to wrap up this section. Next time, we'll come back and talk about some other ideas with redox reactions